How big is infinity? Hi, welcome to FactFusion. Imagine you're back in school, sitting in your maths class. The teacher asks a curious question. Are there more whole numbers or even numbers? It seems like a simple question. You might think, well, there are even numbers and odd numbers, so there must be more whole numbers, right? This is a question that puzzled mathematicians for centuries. It turns out the answer is a bit more complicated and leads us down a fascinating path towards understanding infinity. The intuitive answer, that there are more whole numbers, seems reasonable at first. After all, every even number is also a whole number. But to truly unravel this mystery, we need to dive into the world of one-to-one correspondence, a fundamental concept in understanding infinity. One-to-one correspondence is a fancy way of saying perfect matching. Imagine you have a basket of apples and a basket of oranges. If you compare each apple with exactly one orange and vice versa, without any leftovers, then you know you have the same number of apples and oranges. This principle, as simple as it sounds, holds the key to understanding the size of infinite sets. Let's apply this to our whole numbers and even numbers. We can create a perfect matching like this: 1 matches with 2, 2 matches with 4, 3 matches with 6, and so on. Every whole number has a corresponding even number, its double. This means, surprisingly, that there are just as many even numbers as there are whole numbers. This is where our intuition about size starts to break down when we talk about infinity. We can't simply count to infinity to see which set is bigger. Instead, we rely on this clever matching technique. Now, you might be thinking, all infinities are the same, right? Well, not quite. Enter Georg Cantor, a brilliant mathematician who revolutionized our understanding of infinity. He showed that some infinities are indeed bigger than others. Cantor used diagonalization to prove the set of real numbers is larger than natural numbers. Imagine a list of every decimal number between 0 and 1. Cantor's argument shows you can always create a new decimal not on that list. This proved the infinity of real numbers is denser than whole numbers. Cantor's work opened up a Pandora's box of questions about the nature of infinity. One of the most famous is the continuum hypothesis. It asks, is there an infinity between the size of whole numbers and real numbers? Gödel proved it can't be disproven, and Cohen showed it can't be proven. This means the continuum hypothesis is independent of standard set theory. It's a statement that could be true or false within our current mathematical framework. This discovery showed the inherent limitations of formal mathematical systems. The exploration of infinity has led to profound discoveries in mathematics. It has unveiled a universe of infinities and challenged our intuition. The journey into the infinite continues to inspire and challenge mathematicians. Subscribe to our channel for more fascinating math adventures.